Okay, hello to everybody. So let us go to our sixth lecture, which is about limits of function at the end. It is an important chapter. So we started by introducing the limit for a function defined on a set E, which is a subset of R. So let me just do something different with my iPad today. Okay. Which is a subset of R, and so we have function f defined on E that associates to every x f of x. This is called a real function of a real variable. As everybody knows. And so what is the idea of limit? Of a sequence the idea is a value that is approached here. I use a word which is quite important in this context, and is arbitrarily. Also in a not defined way. So in Italian we say indefinitamente. No? A value that is approached arbitrarily by the sequence the elements of the sequence as n, the label of the sequence, grows larger and larger. This is the idea. So this is the first idea, and extension. We want to extend this notion and generalize from sequences to functions. And to do this extension, there is a remark that is in order now. The remark is that if a function this is an important remark. Let me express it as follows. Since the domain of a sequence is n, which is made of isolated point. I don't want to define what is an isolated point, but it is clear. Then it is clear the variable n cannot approach arbitrarily n, so the element of the domain, cannot approach arbitrarily any real point. N cannot be closer and closer to 3, for instance. N can be 3 or it can be 1 or 2 or 4. However, either n is 3 or n is distance from 3 at least 1. Okay, let me draw a picture to clarify this point. That is conceptually very important. So here you have the real line, here you have natural numbers 0, 1, 2, 3, 4, and so on. So n can be equal to 3 or equal to 2, and there is also distance which is 1 from 2 and 3, 1 from 3 and 4. So n cannot find itself, can never find itself, for instance, here, very close to 3, or here. Vice versa, for functions, the domain can be made in such a way that there are real functions that can be approached arbitrarily. Okay? I write it in green because it is very important. That can be approached so let me say arbitrarily close. Okay, this is a very important point that distinguishes functions and sequences. So now, let me give you an example, a very stupid example. Consider this domain E, which is R minus 0, the real line excluding just the origin, and F defined on E associates to every x the inverse of x with respect to product, 1 over x. Okay, so here, let me talk about the point 3 again. Here, the domain is the whole real line except 0. 0 is not there, but the point 3 can be arbitrarily approached by the variable x. Okay, so in contrast with the previous example of a sequence, with what happens with sequences, here the variable of the domain x can approach the point 3 arbitrarily close. Good. So it becomes meaningful to ask what happens to 3, to the point 3, so what happens to the function as x approaches the point 3 arbitrarily close. Okay, let me give you another example, which is the following. So this time we have a domain which is the whole real line with the exclusion of these two intervals. The interval 0 2 union the interval -2, 0. They are open. And so let me draw it to make it clear what is this set. So here you have 0, which is there. Here you have, which is in the domain. Here you have -2, which is outside the domain, +2. Oh, sorry. -2 plus 2 are in the domain too. Doesn't change anything, but so this is the domain here and here. Okay, so the domain is all this stuff here, including 2, the point 0, and then all this stuff here. Okay. And the function that I'm considering is defined on the domain E with values in R, and it associates to every x the value x squared times x squared by -4. Okay, you see why I chose this domain. I was not obliged to choose this domain, but this is the maximal set in which the algebraic expression I use here is meaningful. Because in order for this expression to be meaningful, this is a square root here, as an argument of a square root, I cannot allow a negative number, okay? And if x is here, between -2 and 2, this is a negative number. But there is the exception of 0, because of course, when x is equal to 0, this parenthesis here gives you a negative number, but here there is x squared that gives you 0. So for x equal to 0, this is 0. This is not a negative number. So it can stand below a root, inside a root symbol. Okay, so this is why 0 can be included in the domain of this expression, but the points between -2 and 0 and between 0 and 2 cannot. So now notice that the message I want to convey is this. So it is meaningless to ask, again in red, what happens to the function as x approaches 0 arbitrarily close. Why? Because x cannot approach 0 arbitrarily close. X that has to remain in the domain of f cannot approach 0 arbitrarily close. Okay, so now you see that the naive idea for which you can take the limit of function only for n going to infinity, of sequences only for n going to infinity, but in contrast you can ask for limits of functions for every point R, for x going to every point in R. This is wrong. This is wrong. You have to consider case by case what is the domain and so on. So there are points in which it is possible to ask what happens as x tends to, which means is pushed arbitrarily close to some number, and there are other numbers for which this question is meaningless. Okay, is it clear? If it is not clear, then go back and listen again to this lecture, because it is an extremely important point. Okay, for what concerns this question, this function, this is the graph. In 0, function is 0, and then in 2 is 0 and then has this form, typical form of a square root. And so I'm very sure that it is like that. No, I'm not sure that the concavity here is wrong, and it is something that is afterwards going like that and so on. So and so here it is completely symmetric. Okay, today I'm a bit distracted, but it is easy so you can understand. Should be something like that. Going to infinity like a parabola. So at the end it will have a curvature like that. However, it is not so important. The message, it is not possible to get closer and closer to 0, to the point 0, remaining in the domain E. Okay? So, we go to the sort of summary of the message of this quarter an hour. The message is the notion of limit can be generalized from sequences to functions asking, the question is, what is the behavior? What happens to the function? What is, again, let me call it asymptotic behavior. This is the word we use for sequences. We can use it also for functions. Behavior of the function f as the variable x moves towards arbitrarily close to a certain point x bar, or grows larger and larger, which means x goes to plus infinity. Or decreases larger and larger towards minus infinity. Smaller and smaller. Along the real line. This is the question. What is the asymptotic behavior of f as x goes somewhere? And be careful that not all x bar in R are good points. Because in some cases they cannot be approached arbitrarily close to x bar. Okay? Arbitrarily close, from the domain of the function. So now what is the problem? So the first task of today is the following. Try to understand, try to characterize So let me say, given a function f characterize all points x bar in R for which it is meaningful to ask whether what is the behavior of f as x gets arbitrarily close to x bar. Okay? So we want to characterize them, to understand who they are. And so, of course, they are points. I repeat it again because I want this idea to be really clear to you. They are all points in R that can be approached. Again, I repeated this arbitrarily close because it is very important. By remaining in the domain. So the intuitive idea is that these points are somewhat attached to the domain, are glued to the domain, even though in some cases they do not belong to the domain. This is the intuitive idea. And the idea, the final notion I will develop is the notion of points of accumulation or accumulation point, which is extremely important. Okay? But in order to give you this notion, I have to introduce another important notion in mathematical analysis, which is neighborhood. Okay, I already talked about neighborhoods in several lectures, and now it is time to give neighborhoods dignity, a specific dignity, and to precise this idea. So the next chapter is called neighborhoods. Okay? The idea is extremely simple. The first, simplest idea of neighborhood is the following. You have here x bar, and you consider all points that are delta close to x bar from the left, so from x bar minus delta up to x bar plus delta, where there are points delta close to x bar on the right. Very simple. This is the intuitive idea, naive. This is the first definition, but then we will extend it because we need a more elastic definition of neighborhood. Okay? Notice that the idea of neighborhood is that in this interval there are no points excluded. This is the first idea. So, definition. Let x bar be an element of R, then the set, I like to denote it by capital I, x bar delta. There are many other symbols in mathematical literature, so don't worry if you consider another symbol. And I becomes a bit from Italian. Intorno is the Italian name for neighborhood, however. I, x bar delta, is the set, exactly the set I sketched here. This is just the set of all real numbers x whose distance from x bar is less than delta. Okay? Notice that it is an open interval. I write here a nota bene. It is an open interval. Of course, you can define it closed. From the point of view of the theory, nothing changes, but in the mathematical analysis, people always prefer to deal with open sets. However, so as I told you, the definition, this set is called the name is spherical neighborhood. This is in the English way of writing. If you're American, you can get rid of this U, sparing a lot of ink, and so being much more ecological and sustainable than Englishmen. So it's called the spherical neighborhood centered again. If you are an Englishman, you write like that. If you are an American, you put an E here, and so you lose your sustainability. Spherical neighborhood centered at x bar and of radius delta. Okay? Just 1 second to notice the word radius, because radius is a word that is usual for circles, and this is not a circle because we are on the line, but if we were in the plane, then the set of points that are delta close to x bar will be exactly a circle centered in x bar. And so the notion of radius will be much more standard than if you are in 3 dimensions, then you are in a sphere and so on. So this is why we use the name radius. Okay, but as I anticipated some minutes ago, this definition is not very good. We need a more elastic definition. So this is the definition of spherical neighborhood, and I immediately give you the definition of neighborhood. So let x bar in R, I say that a set U, which is a subset of R, is called a neighborhood I put the most ecological. I always choose the most ecological version. So in this case, the American one. It's called a neighborhood of x bar if the set U contains a spherical neighborhood of x bar. Spherical neighborhood of x bar, which means that again, so let me cancel this line and let me just take the previous picture. Okay, this is the picture, so we have a neighborhood here of radius delta, and then we can add whatever points we want. So we can, for instance, enlarge this left part of the neighborhood and then add some points, some other interval here, and also a half line here. This U contains the neighborhood centered at x bar and of radius delta, so U is a neighborhood, not a spherical one, but however it is a neighborhood of x bar. last thing I have to introduce, and then we change video. We go to another video, and no, I can stay some minutes here and so conclude this part. So the notation I will use this notation, which is a sort of italics, very elegant. Ux bar is the set of all subsets of R that are neighborhoods of X bar. Okay, this is your X bar. It's called the family of neighborhoods of X bar. Okay, this is the notation. It will be very, very important. And so let me go a bit forward and say some remarks. So first, an arbitrary union. Arbitrary means finite or infinite. An arbitrary union of neighborhood of X bar is, in turn, a neighborhood of X bar. First. Why? Because if you have one neighborhood of X bar, it already contains a spherical neighborhood. So if you add something else, if you perform a union with something else, whatever you add to that, you will always remain with this originary spherical neighborhood. So whatever you obtain will be a neighborhood. Okay, first. Second, more subtle, finite, so not arbitrary, but a finite intersection of neighborhoods of X bar is again a neighborhood of X bar. This is good. Why? Because, let me do it with 2, and the argument immediately extends to every finite number of neighborhoods. So here you have, for instance, X bar, and consider 2 neighborhoods, one which is of radius delta 1, and the other with radius delta 2. And of course, since they are arbitrary neighborhood, not spherical neighborhood, you can add whatever you want. However, when you intersect them, at least the spherical neighborhood with the minimum between delta 1 and delta 2 remains there. When you intersect this guy here, if delta 1 is less than delta 2, remains in the intersection. So what you have is still a neighborhood. And of course, when you intersect finitely many neighborhoods of X bar, you just take the smallest of the radii of the spherical neighborhoods contained in the neighborhoods that you intersect, and this remains there. So the intersection will again be a neighborhood, but this is the subtle thing. Third point. In general, an infinite intersection, so let me be more specific, clearer. So an intersection of infinitely many neighborhoods of X bar is not a neighborhood of X bar. I clarify with an example that you already know because it was an exercise on intervals and intersections. So if you consider the intersection of infinite intersection of all open intervals of this kind, minus 1 over n plus 1 over n, then you get with 0. All these sets that I am intersecting, these are spherical neighborhoods of 0. And this is not a neighborhood of 0. Because there's no delta. Delta will be 0 here. Okay? Let me check whether the set, okay. Let x in R be more specific here and delta strictly larger than 0. Okay, it is better to specify it clearly. Everybody means that this radius must be non-zero, but I want to write it because you are very young, so you need to know everything. Okay, this is the end for this part, for this video, and then I go with the second video and the notion of accumulation point. Thank you very much.